Okay, can you hear me? Yeah, cool. So thanks for coming to my talk. This is a really technical paper. So the goal of this talk is to give an overview of the challenges of the kind of inference problem we have tackled and highlight some of the key ideas instead of giving detailed solutions. So let's get started. I believe many of you have worked with data types in your daily programming, and most likely, the first data type you learned when you entered the world of programming is the list. During the talk, I write code using Haskell-like syntax, but you can easily imagine the declarations defined in languages that you are familiar with. A data type declaration like this defines a type, in this case, a type constructor list, and two data constructors nil and cons. In the comment, I have annotated the type constructor with its type and the data constructors with their types. Getting the kind of a data type is done using one central component in data types, that is kind inference. Kind inference is important because only if we know that the kind of list is star to star, we know that types like list int should be accepted, while types like list maybe should be rejected. However, while we can easily tell the kinds of simple examples like list, we soon get lost when the language becomes more complicated. In recent years, we have seen many feature-rich languages. In the upside, those features increase the language expressiveness, but in the downside, it also raises challenges. For example, given this kind for x, can anyone figure out whether the kind of y should be accepted or not? Let's think about it for 5 seconds. It would be very good of you if you managed to figure it out, but you haven't, that's the point. As the language becomes more complicated, we need a more principled way to understand what those kinds mean before we can conclude that it is actually ill-candid. Therefore, the question we ask, which is also the inspiration of our work, is which data type declaration should be accepted, and for those accepted ones, what kinds do they have? It is important to answer this question because a declarative specification of a data type language is what you might imagine a programmer to have in her head as she programs. And an algorithm can help inform the design of principled inference algorithm for data types. Therefore, we make the following specific contributions. We provide, as far as we know, the first formalization of Haskell 98's data type declaration. This formalization also includes the interesting feature defaulting of Haskell 98. Along the way, we also identified one bug inside the GHC which has been fixed by us. Then, we present a formalization of a fragment of modern Haskell where the type and the kind language is unified and dependently typed, modeling the challenging for type inference, for kind inference in modern Haskell. Along the way, we proposed several technical innovations that are important for the implementation. First, let's take a look at Haskell 98. Haskell 98 has a very simple kind system where kinds are just stars and arrows of stars. That makes things easier as, in this sense, kind inference for Haskell 98 is very close to type inference for simply typed lambda calculus. With the extra support for mutual recursion, in this example, the declaration P and Q refers to each other in their definition body. The simplicity of the kind system also implies that there is no principal kinds for Haskell 98. If we declare this tree data type, because there is no constraints on this type variable A at all, we have many incomparable kinds for tree, and the declarative system would accept all those possibilities. But while those kind of having infinite possibilities is typical for a declarative system, in the algorithm, it is actually a user-facing design decision. For example, in GHC, you can use the kind command to query the kind of a type, and the system must deterministically return a unique kind. Luckily, what to return has already been answered in the original Haskell 98 report, which says that it is possible that some parts of an inferred kind may not be fully determined. And in such cases, a default of star is assumed. Our algorithm faithfully models the defaulting technique. Therefore, using defaulting, the kind of A is defaulted to star and the kind of tree is thus star to star. Defaulting has interesting consequences. To better understand it, let's see more examples. In the left-hand side, we have the data type declaration P1 and P2. We notice that P1 and P2 refer to each other in their definition body. That is, they are mutually recursive, so they must be candidated together. We note that P1 is applied to maybe, so the kind of A is actually star to star, and then the kind of P1 is star to star to star, and the kind of P2 is simply star. So far, so good. Now, suppose the user decides that P1 won't depend on P2 anymore. That is, the definition becomes like this. Now there is no mutual recursion anymore. Instead, there is just a one-way dependency from P2 to P1. So we can separate the counting of the declarations. We can first count P1 and then count P2. Now we notice there is no constraints on this type variable A anymore. Thus, using defaulting, the kind of A would be defaulted to star, and the kind of P1 is thus star to star. Now we go back to P2, and we find that P1 is applied to maybe. Since the kind of maybe does not match the kind of A, the declaration of P2 would be rejected. We see that a slight change of the program can lead to very different results because of defaulting. That is, defaulting could have more impact on the program than you might have expected. Thus, our formalization of Haskell 98 is important to understand this interesting feature. Our paper includes more stuff about Haskell 98, including a declarative specification of the data type language, a sound algorithmic system using the context extension approach. We show that defaulting fits naturally in this approach. We also discussed consequences and design alternatives of defaulting and showed how to restore completeness and principality using kind parameters. This concludes our Haskell 98 system. Now let's move to modern Haskell. We present a formalization of a fragment of modern Haskell. From the kind language, you can see that now we have kind polymorphism. So for the previous tree example, instead of defaulting this A to have kind star, now we can have kind for all K2 star. In this kind language, the type and the kind is unified and dependently typed. So the kind of this type variable A is actually another type variable K. We also have visible kind application where the user can explicitly instantiate a kind variable, but we will skip details about it. To model challenges in modern Haskell, our language also supports many language features, including open kind signature. That is, the user can annotate a data type with its kind signature. Moreover, the kind signature can contain free variables that are not explicitly bound. In this kind signature for D, we have two free variables, K and A, and the system should infer the kind for those free variables and generalize over them. More features that are not covered in this talk, including polymorphic recursion and existential quantification for data constructors. So given this feature-rich language with dependent types, what can you see from this system? Well, I see challenges. So in what follows, I will highlight some of the challenges and give an overview of the key ideas to address those challenges. The first challenge we have is that with open kind signature, in which order do we put free variables in the ordered type context before counting? We need to do it before counting so that the kind signature can be well scoped. In this example for the kind signature of Q, we have three free variables, F, B, and K. We need to put them into the context before we counting the signature, so that the free variables in the signature are actually referring to the variables bound in the context. However, we have many orders you can choose to put these free variables, and we do not know which one to choose. If we do type inference for this kind of signature, we can actually infer the kind of those free variables. Now we notice that the kind of F and B actually depends on K. That is, there can be dependency between free variables. And even though f and b appear before k, since they can't depend on k, we must put k before b and f. However, now we have a problem because we want to put the free variables before canding, but we only know this dependency order after canding. To address this challenge, we extended the type context with local scopes, which are sets of variables that may be reordered. And we propose a moving judgment that reorders local scopes. And then we proved the meta theory of context extension approach extended with local scopes. Challenge number 2, how to generalize unification variables. Suppose we have one type constructor, same kind, that requires its two arguments to have the same kind. Now we see some examples using same kind. Given this kind signature for Q, since there is no kind information for this variable A, we will introduce a fresh unification variable beta as the kind of A. Here we denote unification variables using Greek letters with hats. Since same kind is applied to A, we know that the K in same kind should be instantiated with beta, and the beta should have kind K. But besides that, we have no constraints on beta anymore. So after canding, we will generalize over this cand by introducing a fresh type variable B. Here, beta goes to B, and we get a cand for all B of kind star and for all A of kind B. Notice that the generalization of unification variables are always generalized outside of the whole kind signature. So for this example is good. Now let's see some more complicated examples. Here, the kind of T1 is already complete. So let's try to figure out the kind of T2. Since the same kind is applied to T1 and D has kind C2 star, so we know that the K in same kind should be instantiated with C2 star. And now we want to make T1 to also have kind C2 star. That is, this F in T1's kind should be instantiated with C. And we do not know what this A should be instantiated to, so we instantiated it with a fresh unification variable beta, and we know A should have kind of F, and since F is instantiated with C, we know beta has kind C. It is okay if you didn't follow the flow. The important observation here is that we have an unsolved unification variable beta whose kind depends on a local variable C. Now, if we try to generalize this kind, we will get, by introducing the fresh type variable B, we will again get a kind like for all B of kind C, for all C of kind star. But this is actually EO-typed because C is not in the scope of B. So the problem is, how can we handle unsolved unification variables with dependency on local variables? In this case, we have this beta that depends on C. Our answer is simple, reject it via quantification check. Quantification check means that for a kind like this, after canding sigma, no unsolved unification variable can depend on A. So the previous example would be correctly rejected because this beta cannot depend on C. Quantification check implies that a unification variable after canding sigma is either solved, or since it does not depend on A, we can generalize it outside A. Challenge number 3. Since our language has dependent types, we need to handle unification for dependent types. However, one big difference between our system and most other dependently typed systems is that we only have first-order unification because we want the algorithm to be guessing-free and predictive. There have been studies for first-order unification before, but only the soundness is proved. We argue that first-order unification is still important even in a higher-order setting. For example, a higher-order unification variable for calc favors syntactical equality by trying first-order unification first, because they argue that first-order unification gives the most natural solution. But to our knowledge, they lack a correctness proof. Now let's consider this unification problem. Under this context, we want to unify alpha with beta. We might first try solving beta with alpha. However, this may not be well formed because the kind of alpha K1 may not match the kind of beta K2. So you might start trying to unify K1 and K2 first. But now, unifying a type recurs to its kind. How can we show that the unification actually terminates? And we also have this star of kind star axiom, which seems to further risk termination. To prove termination, we use a novel proof technique based on dependency graph. A dependency graph visualizes the dependency information in an ordered context. To give you a taste of how what dependency graph looks like, here this feature models the dependency graph for this context delta. Using dependency graph, we proved that our unification actually terminates. Our paper includes more stuff about modern Haskell, include a declarative specification and a sound algorithm system. We proved that our algorithm system has principality. That is, while our algorithm does not infer every kind accepted by the declarative system, but the kind it does infer are always the best one. We also include discussions about more language extensions that are beyond the language we modeled here. In summary, we have presented the first known detailed account of kind inference for data types, both for Haskell 98 and for Haskell of today. However, while our system is inspired by Haskell and GHC, our goal is not to faithfully record what's implemented in GHC. Instead, our goal is to produce a sound and complete pair of specification and algorithm. Our technical supplementer include a detailed comparison between our system and what's inside GHC. Along the way, we have also identified ways GHC can improve. For example, instead of doing a quantification check, GHC accepts ensemble unification variables with local dependency using unexpected semantics. But now, since we incorporated quantification check inside GHC, GHC behaves more closer to the system we presented here. And while our system is inspired by Haskell and GHC, we believe that our system is still helpful to inform of the design of principled inference algorithms for language beyond Haskell, as they share many common challenges. But we are the first known to write down those challenges and to formally address them. So that's all I wanted to say, and now I'm happy to take any questions.
Thank you, Ningning. So I don't see any questions on Slido yet, so I'm looking to the audience.
Right, thanks for your talk. Could you comment on how fast kind inference can be, or how slow it can be?
We did not evaluate the performance of the algorithm, but we believe the performance of the algorithm would be very close to those type inference algorithm for dependent types.
You have to be cruel to be kind.
Yeah.
So kinds have been around for a long time. Martin Loeff's type theory has a lot of kinds. He didn't get into the kinds of problems you're describing. So where did we go wrong and diverge from the heaven that Martin Loeff delivered to us?
I'm not familiar with Martin Loeff logic, but I believe that some of the problem goes because of languages like ML actually does not have this kind of star-to-star problem. You only have stars in ML. But inside Haskell, we have those kind of higher order cans, and we need to be careful with these cans, or otherwise the types could go wrong.
Right, but Martin Loeff had higher order kinds.
Yeah, but I don't know how he deals with the cans. Yeah, maybe I will take a closer look to the Martin Loeff framework and then discuss with you.
Yeah, that would be nice, because it's been around for a long time, so it'd be good to understand why things diverged.
Yeah.
Any final question? So, sorry, she wanted to first.
Thanks. So it wasn't totally clear to me why the check that you added that stopped you from kinding certain interleavings of the unification and quantification. Why is that the right thing to do? Because, or maybe the question is the ultimate goal to find a refinement of this algorithm that actually does allow some of these problems?
It does what?
Is the ultimate goal to refine this quantification check so that you can accept more more declarations, because this seems to cut out some that the type inference algorithm currently accepts.
That's totally possible. But it is rather a design choices to do so, because we want the algorithm to be more predictive. But there is, of course, like more complicated approach that can maybe accept those declarations. But the price you need to pay is the system becomes less predictive and more complicated.
Thank you.
Thank you.
Thank you, Ningning. So the next speaker